First, we'll start with the base of the Pantheon. The Pantheon has the basic shape of a dome, so for our sketch, we will need a circle. The half dome becomes cylindrical halfway to accommodate for the rest of the building, which means we'll also need a rectangle to revolve around the same axis. CAD Rotunda. The Roman concrete dome of the Pantheon, weighing 4,535 tons, is supported by a ring of voiceers measuring 9.1 meters in diameter, forming the oculus, the only window at the middle of the Pantheon. The dome's thickness ranges from 6.4 meters at the base to 1.2 meters around the oculus. The height to the oculus and the diameter of the interior circle measures 43.3 meters, allowing the entire interior to neatly fit within a cube, or accommodate a 43.3 meter sphere. When expressed in ancient Roman units, the dome spans 150 Roman feet. The oculus has 30 Roman feet diameter. In this CAD step, revolve the half circle into a half sphere with equal radii for the circle and cylinder. This becomes the inner sphere for developing thickness with another radius. I messed up the other half of the cylinder because I forgot to set up my 2 points on the cylinder and sphere to be the diameter. The oculus is the center of the Pantheon. Its existence not only allows for light, but also operates as a sundial and structural support for the concrete dome. It has a diameter of 9.1 meters or 30 Roman feet. Positioned at the dome's apex, it allows natural light and occasionally precipitation to enter the interior. In the rest of the video, I try to stick as much to scale as possible by making the width thinner on top to mimic the design of the actual Pantheon. The closest I can get is showing the general dome shape. Without the oculus, that point of the dome has the highest tension, from natural shape as well as rainfall. The strategic use of lighter materials at the top, where the dome is most vulnerable, helps reduce stress and potential collapse. The oculus serves both functional and symbolic purposes, allowing light to move around the interior like a reverse sundial and providing ventilation. The Pantheon in Rome doesn't have a traditional gate, as it is an open structure without doors at its entrance. The entryway is an expansive portico supported by large columns, so its height is also 11.9 meters. Each pillar stands an imposing 11.9 meters tall with a diameter of 1.5 meters. The weight of these structures is approximately 60 tons each. There are 16 pillars total, 8 of them arranged in a row and then 3 pillars in every row. On the intermediate block between the portico and the rotunda, the remains of a second pediment suggest that the existing portico is much shorter than originally intended. A portico lined with the second pediment will fit columns with shafts 50 Roman feet, or 14.8 meters tall, and capitals 10 Roman feet tall, or 3 meters, where the existing portico has shafts 40 Roman feet tall, 11.9 meters, and capitals 8 Roman feet, or 2.4 meters tall. The front of the Pantheon is a triangle. On the Pantheon portico there is an inscription which roughly translates as Marcus Agrippa, son of Lucius, having been consul 3 times, made it. Or Marcus Agrippa constructed this while being consul for the 3rd time, although Emperor Hadrian rebuilt the Pantheon one with another message. Here's a diagram of the dome for the Pantheon, and then over here we have about 10 variables. This alpha means angular acceleration, and fiber bundle basically means where the direction of the force is pointing. And then this is in spherical coordinates, naturally, with phi rho and theta, with pressure pointing outwards and force going inwards. Okay, so there's about 10 formulas that we need for calculating the dome's tension. First one's called compressive strength, and by definition pressure is force times area, which means, in this case, the compressive strength of concrete is the maximum load applied to the specimen during the test, over the cross-sectional area of the concrete specimen. The cross-sectional area of a dome is 2 pi radius times height, and since this dome covers the sphere, that means it's 2 pi r squared. So below we also have the tensile strength, which basically means the same thing, and over here I have the pressure calculated for the concrete dome. And then the next 3 are flexural strength, elastic modulus, and Poisson's ratio. This one is also known as Young's modulus. And then these 3 basically determine from this diagram how flexible concrete is, and therefore how much weight it can endure before collapsing at a certain point due to flexibility. For the other 5 formulas, we have shrinkage, creep, density, thermal properties, and durability factor. So epsilon shrinkage is a shrinkage strain. Beta is the coefficient of thermal expansion on the coefficient of autogeneous shrinkage, which we are assuming for concrete. And delta H is a change in moisture content or humidity. For the creep equation, epsilon creep is creep strain at time t. Beta in this case is creep coefficient. T is time of loading. Sigma is a constant, and C is a creep exponent, which is, I think, linear in this case. And then density formula, you know that. And then thermal properties. Q is the heat transfer rate, K is the thermal conductivity, A is the cross-sectional area, which is again 2 pi r squared, and T is temperature difference, D is thickness of the material. And then lastly, we have the durability factor, which is it's like friction coefficient, but it's a factor of how long concrete can last without losing its shape. So on the right, we have the strain durability, and shrinkage, and thermal conductivity of concrete, and then they seem to remain pretty consistent for, in this case, 300 nanometers, just a whole year stabilizing. So the Pantheon stood for a whole year. It's not very likely that this thing will continue to fall. And strain is over here, pretty consistent, and so is the strain in this case, with a consistent temperature. For the floor plan, circles and squares form the unifying theme of the interior design. Their checkerboard floor patterns contrast with the concentric circles of square coffers in the dome. Each zone of the interior, from floor to ceiling, is subdivided according to a different scheme. As a result, the interior decorative zones do not line up. The overall effect is immediate. View your orientation according to the major axis of the building, even though the cylindrical space toppled by the hemispherical dome is inherently ambiguous. There are no sources on the size of the squares and circles, so I eyeballed the sizes. I don't really want to make a circumscribed square inside of another circle, for no less than 50 shapes, so I only did 3 of them on the left for demonstration purposes. The Pantheon's dome exhibits varying thickness, ranging from 6.4 meters at the base to 1.2 meters around the oculus. The construction materials diversify at different levels, starting with travertine at its thickest point, followed by terracotta tiles and culminating with tufa and pumice at the pinnacle. The oculus strategically lightens the load at the dome's vulnerable apex. Tensile tests on the concrete remain unavailable, but Cohen's analysis of Roman's ruins in Libya suggests a comprehensive strength of 20 megapascals. Empirically, the specimen shows a tensile strength of 1.47 megapascals. Finite element analysis by Mark and Hutchinson indicates a maximum tensile strength of 0.128 megapascals at the dome's junction with the outer wall. The dome stresses are significantly mitigated by employing progressively less dense aggregate stones in higher layers. Ingeniously engineered hidden chambers within rotunda, coupled with the elimination of the apex by the oculus, contribute to a sophisticated structural system, reducing the roof's weight. The rotunda wall's upper section features exterior brick relieving arches. Part of numerous architectural devices enhance the Pantheon's structural integrity, cleverly concealed by marble facing on the interior and potentially by stone revetment or stucco on the exterior.